All right. So let's start the lecture today. So many of you have sent me project proposals. I talked to some of you. If you have any questions, talk to me again. Most of the project proposals look good, so keep thinking about your project, work on it. Just as a reminder, I think at the end of March, March 23rd, I think, we'll have short presentations about your projects, right? So people who are taking this class for credit will do a 5-minute presentation. Right? And for the presentation, it's just mainly, 5 or 6 slides, motivation, what you're trying to do, what the approach is, as well as maybe some preliminary results. Okay, so we'll get to see what various people are working on, and you also get to see what others are doing in the class. Okay. If you have any questions about the projects or project presentations and such, I'll give you a little more information next time. But talk to me after the class. All right. And I think that next class I'm going to give you the second assignment, so you'll have 2 weeks or 3 weeks to do the second assignment. So it's going to be a fairly big assignment. So don't start thinking about the project. Work on your project so that you can make your way through the course. I think we only have 4 lectures left. Is that right? That seems about right. Okay. Any questions? All right. So today we're going to be looking at. So in the last class we looked at variational inference methods, right? In today's class, we're going to be looking at sampling-based methods. Okay. How many of you have heard about Markov chain Monte Carlo methods? Okay, most of you. That's good. How many of you have used Monte Carlo methods in your own research? Okay, fantastic. So you should be more or less familiar with these techniques, right? So we'll go through some theory as well as some motivation. So let me just remind you from the last class. Whenever we're looking at the probabilistic graphical models, we're typically going to be interested in evaluating the posterior probability, right? Over some latent variables given observed data. That's generally the case for a lot of models. There are some latent variables or parameters. You're trying to infer the distribution of the latent variables. So for example, in EM algorithm, we have to evaluate expectation of the complete data log likelihood, right, with respect to the posterior distribution. So somehow we have to be able to compute these expectations or have some approximation to the posterior distribution, right? So for complex models, evaluation of the posterior distribution might not be possible, right? Or even computing expectation with respect to the distribution might not be possible. So in the last class, we looked at the variation approximations, right? And as you remember, we've looked at mean field, particularly we looked at mean field approximation and looked at variation Bayesian models. Hopefully that's not going to keep happening. Cancel. So what we're going to do now is we're going to be considering sampling-based methods known as Monte Carlo techniques. Okay. So let me give you one particular example. Where these things are useful. I'm going to give you a couple of examples. This is one very commonly used example in matrix factorization literature. In particular, it's heavily used in recommender systems. So here you have users, you have items, right? You have this big matrix which is very sparse. Users rate items, and what you're trying to do is you're trying to approximate it via low-rank approximation. So you're saying this big matrix is going to be given by the outer product of 2 skinny matrices. Okay? Now the problem is that a lot of entries in this matrix are missing. Right? So if it was a fully observed matrix, you could do something like SVD. But what happens if you have missing entries? Right? So maybe 99.9% of entries are missing. Right? So what you can do is you can say, well, we still can formulate the problem as follows. We can say that let's suppose that R sub ij is going to be the rating of user I for movie J, right? And we're going to have these matrices, which is of size d by n and d by m. So this n and m are number of users, number of movies, and d is some low-dimensional representation. So d, for example, would be typically 20 or 30, right? So the dimensionality of that particular vector is n by 30, and this is 30 by m, right? N could be very large, millions of users, number of items could be large. For example, in Amazon could be millions of items, right? So this whole matrix is a million by million matrix, but you're effectively representing as a million by 30, right? In the order of million by 30. So now what's the goal? The goal is to predict missing values. Right? You want to basically complete the entries in this matrix, and if you can do that effectively, then you can make predictions. Right? You can say who's going to like what items, who's going to like what movies. Right? So what can we do? Well, we can use probabilistic framework to do that. We can say, well, the distribution of a rating for user I and movie J is going to be given by a Gaussian distribution, which is the mean going to be given by the outer product of two vectors. Right? This is known as a bilinear model. You can place Gaussian price over these latent variables. So you can say that all of these user latent vectors are going to be given by a Gaussian distribution, and there are n of them. Same thing you can do for the movies. Right? And this is sort of becomes a probabilistic model. You can also introduce Gaussian Wished price over user movie hyperparameters, which is typically the case. You might not know a priori what these things should be. So you can say, well, there are hyperparameters. You can put private hyperparameters as well. Okay. So this is one of the typical models that you can do. Obviously, you can also use maximum likelihood estimation here by effectively not going through the full Bayesian approach. Is commonly used as well. But it turns out that the Bayesian approach actually in this case gives you pretty good results, much better than if you just do proper maximum likelihood estimation. Right. So effectively what you have is you have sort of this complex model. You have distribution of ratings given the latent factors. You have some private latent factors, right? And you have the price over the parameters of your price. So these are hyperparameters. So now this looks quite complex, right? And this is a graphical model formulation for this model. But now the question is, how can we predict? Right? All we're interested in is we're predicting a new rating for user I and query movie J, right? So here is the case where we can say, well, in order to make a prediction, that prediction is going to be given a user feature vector and movie feature vector. We can predict the rating, but then we have to integrate over the whole distribution, over the latent user feature vectors as well as the hyperparameters, right? So effectively what you have to do is you have to infer the posterior distribution over the latent variables as well as integrate with respect to that distribution. Right? So now it turns out that evaluating this predictive distribution is intractable. In fact, this posterior distribution of parameters and hyperparameters in that model is complicated and there's no closed form solution. So you can't do that. Right? So you need to approximate. So one option, as we've seen in the last class, is to approximate the posterior using factorized distribution Q. Right? That's one option you can go with. You can say, take this posterior distribution and say, well, we're going to approximate it with the factorized distribution Q. Exactly what we did last class. That's a valid option. It actually gives pretty good results. Alternative way would be to resort to Markov chain Monte Carlo methods, right? And that's what we're going to do in this class. And I think that at the end of the class, I'm going to show you why we actually care about getting notion of the posterior distribution. I'll show you that we can actually get pretty good estimates of uncertainties when we're making predictions. Okay, but that's one of the examples where you have some complex posterior distribution of the latent variables, how they interact, and you need to approximate that. Okay. Here's another example. These are known as Bayesian neural nets. I think they were introduced back in the 90s, and Radford Neal, who's a faculty here, was working on these models. Surprisingly, these models, these Bayesian neural nets, I actually they work surprisingly well on a lot of different problems. Scalability becomes an issue in these models, but nonetheless, I know in computational biology people are using them, sort of have become state of the art. Here's the idea. We try to do regression problem, right? We're given a set of IID observations, x1 up to xn, with the corresponding targets. Right? So we're solving a regression problem. We can write down the likelihood, just as we've done in the linear case. We can say, well, the likelihood here, because the data is IID, is going to be given by the product of these Gaussian terms. The mean is going to be given by y, which is some nonlinear function of x, and noise. Okay, that's a standard thing to do. The thing about the neural nets is that this function here is going to be given by the output of a neural network. Okay, so the idea behind neural network is you have some inputs, you take linear combination, you pass them through nonlinearities, typically some sigmoid or 10H nonlinearity. Take the linear combination, and that's your output. Right? So that would be a one-layer neural network. So this is sort of representation of that neural net. Given the input, you compute the activation of the hidden variables, and then you compute the predictions. Okay? But the key idea here is that this function is a nonlinear function of the input, and you have these adaptive parameters, right, that you're trying to feed to the data. Okay? So here, sigma x is a sigmoid function. Right? Now, what we can do with the Bayesian nets, typically what people do is you're using some form of gradient descent algorithm. Right? You can write down the log of the likelihood function, you can use backpropagation algorithm and compute the gradient with respect to these parameters and do maximum likelihood estimation. Right? But the other thing we can do is we can place Gaussian prior over the model parameters. Right? So we're going to say these parameters are going to have a Gaussian prior, right? A Gaussian distribution. Okay? So we have a likelihood function. It's a nonlinear function of the input, as well as a nonlinear function of parameters. We're going to be putting Gaussian prior over the W, right? And then we're going to say, well, what's the posterior distribution of parameters? Okay? And it turns out, you can write down the posterior distribution. There's a likelihood term, there's a prior term, there's a normalizing constant. Turns out that, again, this cannot compute, excuse me, we cannot compute normalizing constant computationally. It's computationally intractable to compute, right? And the reason why it's computationally intractable is precisely because it's a nonlinear function of parameters, right? So if this was a Gaussian, and it was a linear function of W, just like in linear regression model, then we could do everything in closed form. Because we have nonlinearities here, we cannot do it in closed form. Okay? So we need but we also need to compute the predictive distribution. We actually need to be able to approximate the posterior. Right? Yeah.
If you just want to do map estimation, then...
Yeah, if you just want to do map estimation, you can do standard map estimation, yes.
It corresponds to like L2 regularization.
That's right. Map estimation here would correspond to L2 regularization.
But since you want to do Bayesian estimation, you want the full posterior.
That's right. Since we want to do Bayesian estimation here, you actually want to have access to the full posterior. And that becomes very important, particularly if you have some uncertainty about your parameters, right? So you can characterize uncertainties a little bit better. And it turns out when you look at the predictive distribution, this uncertainty helps you a lot in terms of making better predictions.
So like, because regularization doesn't really normalize neural networks, so I was wondering if this really helps.
No, regularization is important. I mean, everybody's using regularizers.
Yeah, but I mean L2.
L2.
The L2 regularization like doesn't really improve
Well, you know, for some problems it does. L2
So I was wondering how like Bayesian treatment is different from, like, does it give much better results or like the same?
Well, the thing is about this particular field, you can actually have access to the full posterior distribution. You can actually characterize uncertainties about your primary values, right? Like you can sample multiple parameters, and that all will give you different models. Right? With L2, you just have one estimate of the parameters. So you know, we'll see some of that in this class. Okay, there's another class of models we've briefly looked at, right? We've looked at undirected graphical models, right? And this is, remember, we've looked at a simple class of models called easy models, where you have binary random vector, +1, -1. You can write down the probability distribution, where you have pairwise terms, you have unary terms, and you have this normalizing constant, right? It's also sometimes known as a partition function. A lot of models in machine learning, again, sort of in undirected graphical models land, they fall into this framework. Markov random fields, conditional random fields, if you've heard these terms, they all basically have a similar structure, and they all have the same problem as how do you estimate the normalizing constant, right? Because that requires you to have this exponential sum, or sum over exponentially many configurations, which you cannot compute, right? So if you have a 100-dimensional vector here, if x is 100-dimensional, then you need to sum over 2 to the 100 terms, right? And that cannot be done in closed form. Sometimes the sum can actually decompose, and for certain classes of graphical models, like tree-structured graphical models, you can actually compute the sum efficiently using dynamic programming, but again, these are sort of special cases. In general, you cannot do that, and so you need to approximate. Right? There's a whole class of whole class of approximation methods. There's a whole subfield within machine learning that effectively are trying to say, well, how can you approximate these partition functions efficiently? Same problem, right? So the way that I want to communicate it to you is that, you know, we've looked at directed graphical models where you have to perform these high-dimensional integrals or sums over exponential many configurations. For undirected graphical models, the same problem, just different meaning. Okay. So now let's look at the notation and get into the sampling method. So for many situations, we're going to be interested in evaluating expectations. Right. Most of the things that we do in machine learning is evaluating expectations. You'd be surprised. You are evaluating expectations. So for example, for making predictions. So typically, we're going to have some high-dimensional integral. We're going to have some function and some probability distribution, and we're evaluating expectations of that function. Right? For discrete random variables, you're going to be replacing it with sum. Right? So I'm going to be using them interchangeably because the meaning basically remains the same. Right? We're going to be using the following notation. For most of the models, the probability distribution can be written as unnormalized probability divided by partition function, or by normalizing constant. Okay? So we cannot evaluate. The numerator we can evaluate point-wise, but we cannot evaluate the normalizing constant. Right? So let's look at some of the models. Remember, when we look at the posterior distribution, the posterior distribution is proportional to the likelihood times the prime. For any given parameter theta, you can evaluate this. If I give the parameters, you can evaluate the likelihood, and you can evaluate the prime. But you cannot evaluate the marginal likelihood, right? Because that requires integral. For Markov random fields, for undirected graphical models, the same story. You have some energy function that you can evaluate. Right? So you can evaluate e to the negative of the energy, but you can't evaluate normalizing constant. Right? So this is sort of a canonical representation that we're going to be using throughout the rest of the class. Okay? Most of the models that basically can be fit into this thing here. You have okay, so simple Monte Carlo, which basically forms the basis for a lot of Monte Carlo methods. The idea is very simple. what you can do is you can draw independent samples from the distribution Ez to approximate the expectation. Right? So here's we can say, well, what we can do is we can draw samples from P, right, and just look at the average. Right? It's very simple. The idea is extremely simple, and that's going to be your estimation of the expectation. It turns out, and it's very easy to prove, is that expected value of F is the same as expected value of your estimator. So your estimate is unbiased, which is good. So the estimator has the correct mean, it's unbiased. If you look at the variance of this estimator, just compute the variance of this guy here, then the variance is going to have this form. That's the variance divided by n. So the variance decreases as 1 over n, the number of samples that you're drawing, which is a very good property to have. So the accuracy of one of the remarks here is that the accuracy of the estimator doesn't depend on the dimensionality of Z. That's a key point. It's a very nice property to have. So great, problem is solved, right? You draw, you can actually show that for a lot of cases, if you have complex problems, and people have looked at these studies, drawing 20 samples can give you very good can give you very good and pretty accurate estimators. Drawing 50 samples, you pretty much can compute these expectations for a lot of problems. So that's very surprising. What surprising result? Is there a catch? Yeah?
What if you have a whole lot of loads in your posterior distribution?
That's true. Not a problem here. We'll come back to that, yeah?
Well, I guess the catch is getting the samples.
Yes. The catch is, can you actually get samples from the distribution P? Right. If I can draw exact samples, and by exact meaning that I can actually draw samples from this distribution, IID samples from this distribution, the problem becomes fairly easy to solve, as it turns out. As we'll see, there is no magic trick here that most of the models we will never be able to draw exact samples or IID samples from that distribution. That's where the problem comes in. So high accuracy, you can achieve high accuracy with a small number of independent samples. And problem 1, we may not be able to draw independent samples. Right? And we'll see that will be the problem. And problem number 2, it can be the case that our function is large in the regions where the probabilities are small. Right? And the other way around, then the expectations may be dominated by regions of small probability. And so you need much larger sample size. Right? Say, your function takes very large values, but the probabilities in that space are very small. Nevertheless, when you compute expectation, that sort of comes in. Right? So you might need to draw more samples. That's another problem. And in general, there could be potentially cases where, this is sort of cartoonish illustration of, which is a big problem for a lot of different methods, is that you might have some probability space, and you might have some peak in a small, narrow part of the space, and it actually might contain a lot of mass. And if you don't find it, it's like it doesn't exist. Right? So that's a problem. But let's look at the predictive distribution, right? And in general, in a lot of cases, when you look at your predictive distribution, you have a likelihood, you have a posterior. So you might say you can approximate this interval by using Monte Carlo approximation. Right? These samples are drawn from the posterior. Right? So that's a Monte Carlo approximation. But again, it's going to be hard to draw samples from the posterior. Right. In fact, it's very unlikely that you'll be able to draw IID samples from the posterior distributions, unless you can compute these posterior distributions exactly, have a closed form solution. Right. So that's going to be generally the case for us. But you can see that, looking at the predictive distribution, how we can use Monte Carlo integration. Okay? Now, let's quickly look at the directed graphical models. We've seen that before for many distributions. So the joint distribution, let's say this is your observed data and these are your latent variables. You can actually sample from the joint distribution. So for directed models with no observed variables, if you want to sample from the distribution, you sample x1, x2, x3, you sample x4, x5, conditional on the samples of the parents, and then the parents' variables are set to the sampled values, and then after one pass, you get samples. So the nice thing about directed graphical models is you can draw samples from the model. Right? You can instantiate parents, children, all the way down to the observed data. But remember, when we've looked at directed graphical models, most of the times we're going to be solving the problem where some of the nodes are observed. So let's say this is your data. You get to observe the data, and you want to infer the posterior distribution over the latent variables. Right? So here's one naive idea how we can do that. You want to sample from the joint, so sample from the model. If the sample values agree with the observed values, then we retain the sample. Right? Otherwise, we disregard the whole sample. So you're drawing samples from the model up until you agree with the data that you see. Right? This algorithm samples correctly from the posterior distribution. Any guesses why? Well, it does sample correctly from the posterior distribution because you're drawing samples from the model, and if for one particular sample you basically agree with the observed data, then these are the samples, correct samples from the posterior, right? Those are the samples that gave rise to the data. But the overall probability of accepting such a sample is going to be decreasing rapidly, right? As the number of examples increase, or the number of data, the number of dimensionality of your data increases, right? Think about computer vision application. I can give you a computer vision application. Imagine that you have some latent variables that are specifying in this room how many people there are, how many desks there are, how many tables there are, which locations each desk is located at. Right? And then I take a picture of this classroom and I want to infer how many desks there are, how many people there are, where are they sitting and such. So it's a complex procedure, right? So using that particular model, what I could do is I could just say, well, sample the number of people, sample desk, sample arrangement, generate. Is my image looking like the picture that I'm seeing? No. Keep doing it up until you hit the right thing. Right? Once you actually generate what I'm seeing here, then that's the correct answer. Now, obviously, you can see that it's not going to be very scalable, but that's a valid procedure. Now, let's look at the basic sampling algorithms. Okay, this is sort of statistics 101. Can you generate samples from non-uniform distributions, simple non-uniform distributions, assuming you can generate samples from uniform distribution? Let's make an assumption that we can actually generate samples from the uniform distribution, which is debatable whether you can or not, but let's assume that we can. So what we can do is we can define the cumulative distribution function. Right? So this is, let's say this is what we're trying to get a sample from. You can construct a CDF. You can sample Z from uniform, and then just invert the function back. In this case, Y is going to be a sample from P. Right? So problem solved. Is that right? What's the problem here? It looks like if I draw samples from uniform, I can sort of just convert and get a sample from this bimodal distribution. Yeah, there was one in the back.
No, I mean, the problem is that as soon as you have atoms or sort of sets of null, like this only works if you have uniform positive probability. Because otherwise the inverse just doesn't exist. I mean, then you have
No,
examples.
let's make an assumption that the inverse exists, and you can compute this.
The particular solution.
Yes. The problem is that computing this CDF is just as hard as computing the original P. So there is no magic here. But let's look at one example. So this is an exponential. In this case, turns out you can compute this integral, which is the CDF of the exponential. You can sample z from uniform 0, 1, invert it back, and that's going to be a sample from the original distribution. The problem is that computing CDF is just as hard as getting sample from the original distribution. Right? So there is no magic here. But this is sort of a one way of thinking. You know, if you have in your code, if you can generate random numbers, you can generate from simple distributions, you can generate samples. Let's look at rejection sampling. So rejection sampling is another way of sampling. So let's say that we're going to be sampling from some target distribution P, right? And let's say the target distribution P is difficult to sample from. It's P tilde divided by normalizing constant. But suppose we have an easy to sample proposal distribution Q. So we're going to propose the Q distribution such that that condition is satisfied for all Z, right? So what is this condition? This condition is effectively saying that you have some easy to sample distribution that basically covers your original distribution, right? For some constant K. That condition has to be satisfied. So what can you do? Well, you can sample Z from Q, right? You can sample Z from your proposal distribution. And then, so let's say you sample from your proposal distribution, this is your sample, right? And then you sample U uniformly from 0 all the way up to the upper bound, K times Q of sub 0. And if you can show that this sample, Z and U, has uniform distribution under this curve, under the blue curve. It's effectively a definition of getting samples from the distribution, right? If U here, the sample, is in this part of the space, you're rejecting it. So if U is bigger than the P hat here, then the sample is rejected. If it's below, the sample is accepted. Right? Makes perfect sense. What's the intuition here? You join uniform samples under the blue curve, and then you're basically saying, for that particular sample, am I under the red curve or not under the red curve? Right? So what's the probability that the sample is accepted? Well, the probability is going to be calculated as follows. What's the probability? You sample from Q, so you're taking expectation with respect to Q, and you're looking at the ratio of this quantity divided by the total. Right? That's the probability of being accepted. Right? If you can come up with a blue curve that perfectly matches the red curve, then it's like drawing exact samples from the distribution. So your acceptance probability is always going to be 1. Right? If you compute this quantity, this is just going to be that expression here. So the fraction of accepted samples depends on the ratio of the area under P tilde and the ratio, the area under the Q distribution, right? Under the blue curve. Right? Everybody sees that? But it's often very hard to find Q distribution with optimal K. That's one of the biggest problems with rejection sampling. Here's one example. Let's say that your target distribution is a Gaussian distribution with some variance. Okay? And let's say your proposal distribution is Q distribution with some other variance. Okay? You have to make sure that the proposal variance is bigger than the variance of the target distribution, right? In order to satisfy the condition, right? Because these guys have to cover, the red curve has to be on top of the green curve, right? And the optimal K here, you can show, is going to be given by the ratio of the two raised to the power of D, if you're working in D-dimensional space. So the acceptance here is going to be diminishing exponentially, even for such a small problem. Right. And typically what we will see is that you'll see that rejection sampling is typically used in 1 or 2 dimensions. And in most of the cases, you can use it as a subroutine in more advanced techniques. Right. Now, insofar with rejection sampling, one of the problems with rejection sampling is that you're drawing samples and then you're discarding them. Right? Here is another technique called importance sampling. And this is by far the most heaviest used technique in a lot of different methods. The baseline technique for a lot of different methods. Here's the idea behind importance sampling. It's a very simple idea. Suppose you have an easy-to-sample proposal distribution Q. Right? So you have Q distributions you can sample from the distribution, such that the only condition you need is Q has to be non-negative if P is non-negative. Right? Obviously, that has to be the case. If Q has 0 probability in some regions of the space where P doesn't have 0 probability, then you will never get the right answer. Right? Suppose we're trying to estimate this expectation. Right? Well, what we can do is we can multiply and divide by Q. Right? And this is where the condition of positive probability mass comes in, because you don't want to divide by 0. Right? Now, what you can do is you can basically say, well, now I can draw samples from Q, right? And I can use Monte Carlo approximation to approximate this quantity here, right? So it's 1 over n, this guy, right? And these quantities are known as importance weights. So these quantities, the ratios P over Q is known as an importance weight. Unlike rejection sampling, all samples are retained. So in this case, we're actually using all the samples. We're not getting rid of the samples. All samples will enter into the equation. So one of the problems here is that, again, typically we will not have access to P, right? We'll only have access to P tilde. Right? So what can we do in this case? So let's say our proposal distribution of this form. Q is some proposal distribution. Typically, we will know the partition function for Q distribution. Right? We can think of Q distribution as being a Gaussian distribution. Right? We've seen so far that expectation can be written this way. Right? I multiply and divide by Q. Then I'm using my expression saying Q is Q tilde over partition function, P is P tilde over partition function, so I can push out these partition functions out. And that's my expression here. And so now, using importance sampling, I can say, well, this is just importance sampled, and then I have the ratio of partition functions. Right? But you can use the same weights, same importance weights to approximate the ratio of partition functions. Right? Because what is the ratio of partition functions? Well, look at the ratio, 1 over qz, that's the definition of partition function, it's the integral. And now what you can do, this is the same as divide by q tilde times q. And this is nothing more, it's just the average of the importance weights. Right? So now, what you can do is you can estimate the expectation of the function by looking at the importance weights, but these importance weights are now normalized. That's the key, right? So this estimate is consistent. Consistent meaning that as n goes to infinity, you'll get the right estimator, but it's biased. So its expectation is not equal to the true expectation. Any guesses why it's biased? This estimation here is unbiased. If I really want to estimate the ratio of two partition functions, that estimate is unbiased. Its mean is the correct mean. This estimation here is unbiased. If I knew the ratio of partition functions and I just wanted to estimate the expectation, that is unbiased. The trick is that when I take the ratio of two unbiased estimators, the estimator becomes biased. That's the thing. Right? So if you have two unbiased estimators and you divide them, you get a biased estimator. The mean is not quite right. But nonetheless, it's a consistent estimator, and this is one of the tricks. So a lot of different algorithms, a lot of different sampling algorithms basically fall into this kind of framework. Right.
What's the definition of consistency?
Consistency is essentially says that as n becomes sufficiently large, you will converge to the right estimator.
But if the expectation is not the same,
Well, what it basically means that consistent basically means that as n goes to infinity, you will get the right mean and the variance will shrink. So you will get the right answer. Bias basically means that on average, so if you take two estimators and you average them.
The expectation of the estimation is equal to the true.
No. So now, one of the questions is that one of the problems with these estimators is that it's very hard to estimate how reliable the estimator is. In particularly, one of the biggest problems with this estimator, and it's a work of a lot of research happening in the area, is the variance. Huge variance. If the proposal density Q is small in the regions where FP is large, then you get into trouble, right? Because you're sampling from the model, you get some estimators. Once in a while, you sample in a part of the space that's very unlikely. And if in that part of the space you have a huge number, then you're basically getting, reasonable. Once in a while, you have a huge number. And, you're taking averages and the whole thing just collapses, right? Here's one example. So this is using a Gaussian distribution as a proposal in 1D case. This is the number of millions of samples. So, you sample initially, the estimator goes up and down. Here it looks like it's converging. Right? And this is the truth. And then again, here it looks like it's converged. There's a lot of samples where you look at the averages, looks like it's stable. And then again, it's just diverges, right? So that's one of the biggest problems, how to come up with a good proposal distribution. Right? On the other hand, if you're using Cauchy distribution as a proposal, which has heavy tails, so after 500 samples, the estimator basically converges to the right value. So one of the key things when you're using these methods is that your proposal should have heavy tails. That's one of the things. So you want to cover as much space as possible. Okay. Now, again, these kinds of techniques are being used in 1, 2D spaces. Typically, if you're working in high-dimensional spaces, these techniques will have huge variance. Now, let's just look at the Monte Carlo EM. So, now we sort of covered a little bit of sampling, right? But in general, and in the last class, we looked at the variational inference, right? So we've seen how we can use variational methods to approximate the E-step in the EM algorithm. But here we can also use Monte Carlo sampling to approximate E-step of the EM algorithm. So for example, if we give an observed variable x, hidden or latent variable z in the model parameters, in the EM step, we're typically maximizing the expected complete data log likelihood, right? In principle, what we can do is we can approximate this integral this way, and by drawing samples from the posterior. Right? That would be a Monte Carlo approximation of expected complete data log likelihood. So we're drawing samples from the posterior and the average with respect to the joint. Right? So the samples are drawn from the current estimates of the posterior distribution, and then the Q function is optimized in the usual way. Once you have a Q function, you can differentiate the respective parameters. It's a very heavily used technique with a lot of different models. Right? Maybe you can draw samples from the posterior, maybe you can draw approximately samples from the posterior, but that's commonly used technique. Here's one particular algorithm called the IP algorithm. I think it came out from the statistics community back in the late 90s. But let's suppose that you're moving from the maximum likelihood approach to the fully Bayesian approach. right? So we'd like to get samples from the joint posterior. So let's say not just samples from the latent variables, but we also want to get samples from the full posterior distribution of the latent variables as well as parameters. But this is difficult. That would be difficult because latent variables and parameters are typically coupled together. What we're going to be making assumption is that we're going to assume that it's easy to sample from the posterior of the parameters given the latent variables. Right? Think of a mixture model. If I tell you which component each data comes from, sampling from the posterior of a means or the covariances becomes easy, particularly if you're using conjugate priors. Right? And this is inspired as a so-called data augmentation algorithm, which alternates between two steps. There is an imputation step, analogous to the E step, and there is a posterior update step, which is analogous to the M step. Right? And let's look at the two steps. In the imputation step, you want to sample from over the latent variables. You want to sample over the latent variables, but with parameters marginalized out. And we cannot do it directly. And that's the definition, right? This is the posterior given the parameters. There is a posterior over parameters, and you're integrating over parameters. So here you join over the latent variables with parameters integrated out. So what you can do is you can approximate it by joining samples from the posterior and then join latent variables given the sample from the posterior. A lot of Monte Carlo techniques are going to be working in the same sort of spirit, where you can draw multiple quantities sequentially, right? So you can draw that. We're making an assumption that you can draw from the posterior. You can draw the latent variables given the parameters. For the projection step, you can use the following relation. You can say the posterior of the parameters is given by the posterior of the latent variables, and the posterior of the parameters given latent variables, but with latent variables integrated out. Right? And so here, again, the same property. If you join samples Z here from this distribution, then you can approximate the posterior. Right? So sort of nice, nice quantity. Right? And here, which is by assumption is easy to sample from. So this is something that we can sample from. That gives us the approximation to the posterior. And then given this approximation to the posterior, we can draw theta. So this is something that we can sample from. So you're drawing theta, you're drawing latent variables, and you're sort of alternating between the two. Right? So, summary so far, one of the things to keep in mind is that if the proposal distribution Q poorly matches the target distribution P, then rejection sampling almost always rejects. Right? If there is a mismatch between the two, you'll just be wasting your computing time. Important sampling will have large, possibly infinite variance, and you'll get unreliable estimates. So for high-dimensional problems, finding good proposal distribution is extremely hard. It's very hard to come up with a good proposal distribution, so what can we do? And the answer to that is using microchain Monte Carlo methods. So before we jump into MCMC methods, let's just take a 10-minute break. In the second half of the class, we're going to go through MCMC methods. Okay, why don't we continue? Right. So the second part of the lecture, we're going to look at the the basic, the fundamentals of Markov chain Monte Carlo methods, just give you a little bit of intro to these methods. Obviously, you can teach the whole class on these methods, and there's a lot of research happening in that area. But let's look at it from the basics. So, first order Markov chain. Imagine that you have a series of random variables z1 up to zn, such that the following conditional property holds. We're going to be saying that the probability of the z random variable n plus 1 random variable conditional on all the previous other random variables is just given by this conditional probability, right? Where you're just conditioning on the previous one. So effectively, the intuition here is that the future only depends on the present, and you're disregarding the past. Right? That's the intuition. Now, we can specify the Markov chain in the following way. We have to have a probability distribution for the initial state. Right? This is the probability distribution of Z1. It's the first state. And then we're going to be specifying conditional probability for subsequent states in the form of transition probabilities. So these are going to be what's the conditional probability of Zn plus 1 given Zn. And we're often going to be using T notation for the transition kernels. So sometimes people think of T as the probability of going from Zn to Zn plus 1. Okay? Think of these transition kernels as conditional probabilities. It's just in our notation, sometimes it's going to be easier to use T as a transition operator. Now, the marginal probability of a particular state can be computed as follows. So if you compute what's the probability of being in state Zn plus 1, well, it's the probability of starting at Zn, transitioning to Zn plus 1, and summing out over Zn. Right? If you look at this, there's nothing particular. It's like specifying the joint probability and marginalizing out one of these random variables. Right? But that's the probability of the marginal distribution. Now, a distribution pi is said to be invariant or stationary with respect to the Markov chain if every single step in the chain leaves pi invariant. That's the notion of invariance. And that's the definition of invariance. If you say you start at some state with probability pi, you apply the transition operator, the distribution remains invariant. Right? So you're basically getting pi of z. The intuition you should have here is that if you start with distribution pi and you apply transition operators, you basically stay under the same distribution. Again?
So just to be clear, I think you already said it, but the transition, that's the probability of going from Zn to Zn plus 1?
So this is probability of moving from Z prime to Z. Yeah. Okay? And that's a notion of invariance. Right? That's a key notion. So a given Markov chain can have many stationary distributions, pi. So for example, let's say you have a transition operator, which is just the identity. Okay? It's not very interesting transition operator. It basically says, stay wherever you stay. Stay wherever you are. Don't do anything. It's the identity transformation. Then any distribution is invariant. Right? Obviously, plug in any distribution. You just say, stay where you are. That's given by pi z. Right? So in principle, a given Markov chain may have many stationary distributions. Now, sufficient but not necessary condition for ensuring that pi is invariant is to choose a transition kernel that satisfies a detailed balance property. Right? Again, just as a reminder, this is given by the conditional probability. And this is the detailed balance property. Right? This effectively specifies the joint distribution of z prime z, and this also specifies the joint distribution z prime z. Okay? But the intuition here is that you're starting at z prime, you're moving to z, or you're starting at z and moving to z prime. Okay? That's a detailed balance property, and a transition kernel T that satisfies detailed balance will basically leave the distribution, that distribution invariant, right? And you can prove that. Here's the proof. If I look at this expression here and I sum out Z prime, okay, I'm replacing this guy here, still sum remains. It's the definition of detailed balance. I can pull out phi out, and what is this? This is just 1, by definition. Right? That's given by the conditional probability. So that's 1, you get pi z. That effectively means that that transition operator leaves pi invariant. Okay? A Markov chain, and also a Markov chain that satisfies detailed balance property, it's the property, is said to be reversible. So these are known as reversible Markov chains. It's not a necessary condition, but it's a sufficient condition for leaving pi invariant. So sometimes, people design certain transition operators and they say, okay, is these transition operators leaving my pi distribution invariant? One thing you need to do is if you check detailed balance, and it checks out, then it's then it will leave pi invariant. And this is known as a reversible Markov chains. There's a whole literature on non-reversible Markov chains, but reversible Markov chains are the most commonly used at least in machine learning. A lot of standard techniques using that. So let's look at some examples. So let's look at the discrete example. Let's say I'll station a distribution pi star. So the probability of being in state 1 is 3/5, and second state 1/5, and third state 1/5. We define a transition matrix T, and Tij is the probability of moving J to state I. So these numbers sum to 1. That's the probability of, being in state 1, moving to state 1, being in state 1, moving to state 2, being in state 1, moving to state 3. Right? They all check out. They sum to 1. In this case, P star is invariant distribution with respect to its transition matrix T, because you can show that T times P star equals P star. Okay? Or, in other words, that condition holds. And that's the definition of the stationarity, right? You take P star, you apply the transition kernel, you have P. P is also equilibrium distribution. It's an equilibrium distribution. The reason why it's equilibrium distribution is that if you start at any state, so let's say we're starting at 1, 0, 0, and you apply this transition operator, in this case 100 times, you get P star. If you start at 0, 1, 0, if you start at any other state, after enough transition operators, you will reach P star. Once you add P star, you'll stay at P star because of this condition. Right? So the intuition here is that you start at some state, you apply these transition operators, you will reach the stationary distribution. And that's equilibrium distribution, stationary distribution for that transition operator. Okay? So one question is that, okay, so why is this useful to us? Any guesses, why is this useful to us? How do we specify? Yeah, go ahead.
Well, you find a Markov chain which has its equilibrium distribution, whatever you want to sample, and then you just keep.
Yes, that's exactly right. So this is what we're going to do. We're going to say, well, let's say we want to sample from some target distribution, which might be a posterior distribution in your Bayesian probabilistic matrix factorization model, or it might be a Markov random field. You want to sample from your MRF. So you define your target distribution pi to be pi tilde over z, and then, as we've seen before, obtaining independent samples is difficult, but what we can do is we can set up a Markov chain with transition kernel T that leaves the target distribution pi invariant. Okay? That's the goal. If the chain is ergodic, and I'll define what that means, then the chain will converge to this unique equilibrium distribution. So you're setting up the key idea is that you're setting a Markov chain in such a way, and you have to specify what the transition kernel should be, in such a way that if you're running this Markov chain, eventually it will converge to this distribution. And if it converges to that distribution, we'll see that you can draw samples from that distribution. Okay? Now, we will obtain dependent samples drawn approximately from pi distribution by simulating Markov chain for some time. Okay? Now, ergodicity. What is ergodic? Well, ergodicity essentially requires that the definition is that it requires there exists some k such that for any starting state, there is a non-zero probability that we will reach any other state. That's roughly the definition, right? After some number of transition steps, you'll have a non-zero probability of moving into some state z prime for which pi of z prime is non-zero. The intuition here is that effectively you will explore the whole space. There's always non-zero probability of reaching any state in your domain for which pi of z is non-zero. Right? Intuitively, it makes sense. If you're setting up a Markov chain and can never reach that one particular state for which your station, your pi, has non-zero probability, then you'll not get the right answer, right? That's the intuition. And the proper definition is that state I is said to be ergodic if it's eperiodic, positive recurrent, and so forth. So you can look at the book a little bit, the definition. There is a definition of all states. I guess all states in the reducible Markov chains are ergodic, and the chain is also said to be ergodic. So it has to be positive recurrent, basically meaning that there's some probability of returning to the same state after a certain time, and it has to be aperiodic. These are sort of a little bit more technical definitions. For our purposes, most of the cases, the way that people define these transition kernels are effectively going to have that property. And we'll see some of that. Okay? Now, one of the key principles here is that in practice, we can also construct the transition probabilities from a set of base transition operators, B1 up to Bk. One option is to consider mixture distributions of this form. It's a very commonly used technique in practice where you have multiple transition operators, and you're basically saying your overall transition operator is going to be looking at a mixture of these base transition operators. Okay? And there's mixing coefficients, it's almost like a mixture model. Another option is to combine base operators through successive applications of these base operators. You apply the first operator, second operator, and so forth, up to the kth operator. Okay? If the distribution is invariant with respect to each of these base distributions, then it will also be invariant with respect to these combined operators. Right, that should be sort of trivial. We'll see some of the applications of that technique here. Let's look at the first case. So if we look at the case of the mixture model, if each of the base distributions satisfies the tail balance, then the mixture transition T is also going to be satisfying the tail balance. Okay? Now that should be obvious because it's just a sum. It turns out that if you combine transition operators using these composite transition probabilities, then if each one of these operators is reversible, the combined one is non-reversible. Any guesses why that is the case? It's the intuition. I guess I can show you one particular intuition here. Let's say you have a probability density that looks like this. Okay? I guess people looking at live can't see it, but the intuition here is that, let's say I start here. Okay? And what I have is I have two base operators. One is sampling across y for a given x, and the other one is sampling across x. So I'm looking at two dimensions, and I'm sampling across one of the dimensions. Right? If I sample along this dimension, and let's say I end up being here. Let's say it looks like this. Say I sample here, and I end up here. And then I sample it along here, which is another axis, and I end up here. Right? Now, what's the reversibility? The reversibility essentially says, well, if you're moving here, then if you apply the same set, how do you move from here back here? Well, from moving from back here to here, you would have to go here and then here. right? Obviously, you can't do that because the probability of going here is 0. So the only way for you to do is to sort of reverse and go back here and here. Yeah?
Does that imply that you need a convex distribution?
No. So this is the case that it's non-reversible, meaning that you first sample along y, then x, and that's how you got here. If you're starting here and you want to go back here, you have to reverse. So you can't just sample x and y to get back here. The probability of using using the same base operations is 0. But so what people do is people typically symmetrize the order of application of the base transition operators. So you start with B1 to BK, and then you apply again BK, going all the way to B1. So in this case, then, if each one of the B's is reversible, the whole composition is going to be reversible. Right. So, and this is a very common technique using these composite transition operators, where each base probability changes, each base transition changes only subset of variables. So typically, if you're working with very high dimensional problem, you can, in principle, take a subset of variables, apply MCMC to only subset of the variables. In particular, one of the things that we're going to look at is the Gibbs sampling operator. It basically picks one dimension, moves along one dimension, picks another dimension, moves along the other dimension. Okay. Now, one of the most popular techniques, and I'm sure many of you have heard about Metropolis-Hastings algorithm, right? How many of you have heard about Metropolis-Hastings algorithm? Right, good. It's a Markov chain transition operator. You know the story behind Metropolis, right? That technique was developed while a bunch of really smart guys were in Manhattan Project, working in Manhattan Project right now. These guys developed nuclear bomb. And that's where the technique was developed. The funny thing is, it requires the notion of random sampling to design the algorithm. At that time, I guess they didn't have computers, so they were simulating random numbers by flipping coins. So there were actually people flipping coins to sort of apply this algorithm. The other interesting fact, I don't know if you know Hastings. Hastings was a student here in Toronto who basically did the modification of the original Metropolis algorithm. So that's an interesting fact. I didn't know about that. He was a student. His thesis was on sort of that particular idea. I think he was with Department of Mathematics here. Anyways, so let's look at the MH, Metropolis-Hastings algorithm. So the Markov chain transition operator from the current state Z to a new state Z prime is going to be defined as follows. We have a new candidate state Z star, which is going to be proposed according to some proposal distribution Q. Okay. So Q could be whatever proposal distribution you want to be. We'll look at some examples, and then we're going to say that this candidate Z star is going to be accepted with this probability. Okay, so what is this probability? This is the probability, to look at the first ratio. This is the ratio of the new proposed sample divided by the old one. And Q here is the probability of moving from the new to the old. And this is the probability of moving from old to new state. Okay? So it's sort of, we'll look at some of the examples. We'll see why this is important. It's a correction term. If we accept, so obviously that's going to be a number. Okay. We take the minimum of that number in 1. Obviously we can't go beyond 1. And then we're going to be sampling according to this probability. Okay. If accepted, then we're going to be setting the new state to Z star, the one that we sampled from Q. Otherwise, the next state is just going to be the copy of the current state. Otherwise, and that's important. It's not like we're disregarding the sample. We're actually saying the next state is going to be the copy of the old state, the current state. So your samples from Metropolis-Hastings algorithm would look like, let's say you're sampling, you might sample 3, 5, 8, and then it's going to be like 8, 8, 6, 7, 7, 7, 7, 8. Right? If you're rejecting, you're considering the next state as being the old state. Okay? Notice that there is no need to compute normalizing constants for pi. That's important. We're making assumption that p tilde is something that we can compute. Right? For symmetric proposals, which was the original Metropolis algorithm, so for example, if you say, well, I'm going to be sampling from a Gaussian distribution, my proposal is going to be a Gaussian distribution centered at my current state with some variance, then the acceptance simply reduces to this ratio. Okay? And this sort of has a good intuitive meaning, right? What does this say? If I have a proposal distribution and I sample something that's actually more likely under my posterior distribution than to something that I had before, this is going to be greater than 1, which is good. I'm moving to the part of the space where I have high probability under my target distribution, right? And you're moving there. Right? If you sample something that has low probability where you're currently sitting at right now, if it has a little bit of low probability, so say this is 1/2, then you're flipping a coin, you're saying with probability 1/2 move to this new state. Right? Otherwise, you're staying where you are. Now, it turns out that you can show that the MH transition kernel, this is the kernel defined by MH, leaves pi z invariant, and you can show it by showing that it actually satisfies detailed balance. Right? This is one idea where you're designing this kernel. This is the case where you're designing a transition operator that leaves your pi invariant. Right? And you can prove that it satisfies detailed balance. If you can prove that it satisfies detailed balance, that's it. It leaves the distribution invariant. That's what you want. So here's the proof of detailed balance. It's actually pretty trivial. You start at pi z, this transition operator z prime, going from z to z prime. Now, what is the transition operator? The transition operator is given by this expression here. Right? What is the transition operator? Remember, you're sampling from your proposal, and you're accepting with this probability. That's your transition operator. Right? So here, you're effectively taking this, putting it inside the mean operator. You rearrange the terms, you're pulling out this out, you get this expression, and this is exactly the same as starting at z prime and applying the transition operator the other way around. One thing is that the chain, whether the chain is ergodic or not, is going to be depending on the particulars of the station distribution pi and proposal distribution. Okay. So you just have to make sure that your proposal covers all the states, has non-zero probability of reaching all the states for which pi has non-zero probability. Okay, so that's you can look at. I think that in one of your homeworks you will prove something like that for one of the transition operators, so you'll get a little bit of hands-on experience with that. Here's how Metropolis Hastings algorithm works. Let's say you want to sample from a Gaussian distribution with proposal Q. So this is your Gaussian distribution. Your proposal distribution is going to be a normal distribution with some variance centered at the current state. So notice what happens here. The green points are the accepted points. The red ones are rejected points. It's interesting to note that, let's look at this guy here. If you're moving this in this part of the space, it's accepted. If you're moving in this part of the space, it's rejected. Right? So you can see that it mostly explores the space under the Gaussian distribution, which is roughly what you want. Now, there's one particular problem with this algorithm. There are always problems with the algorithm. Right? We had a perfect algorithm, we wouldn't be studying that, right? But let's look at a random walk behavior, which is a problematic thing when you're choosing the proposal distribution. Let's say you have a state space consisting of integers, right? So 1, 2, 3, minus 1, minus 2, minus 3. Let's say the probability of staying in your current state is 0.5. The probability of moving to the right is 0.25. Probability of moving to the left is 0.25. Okay? So you're sort of moving along the integers. Let's say the initial state is 0. Okay? You start at 0. Then by symmetry, the expected value, because you symmetric walk in both directions, the expected value of zt is 0. But it turns out that the expected value of zt squared, which is effectively the variance because the expectation is 0 here, is going to be given by t over 2. Okay? So, roughly, what does this say? This says that after t steps, roughly, the random walk will have traveled a distance that's an average proportional to the square root of t. Okay? And this square root depends on the typical behavior of the random walk. Right? And that's sort of like the worst case setting. It basically says, well, ideally we'd like to design MCMC methods that avoid this random walk behavior. Right? So to, which basically, this is basically saying that if you want to travel distance t, you need t squared steps. Which is bad. So let's look at this example in particular, just to make it a little bit clearer. Suppose our goal is to sample from this correlated Gaussian distribution. That's what we want to sample from. And let's look at the Gaussian proposal distribution centered on the current state. So we say, this is our proposal. Let's say we're here. That's our proposal distribution. What happens in this case? Well, if the variance is large, if we make it big proposal, then almost always we're going to be rejecting, right? If you make the variance small, very small, then your Markov chain is going to be moving very slowly. And that's one of the common problems. Like in general, you will not know what the red distribution looks like. It might be some complex distribution. And then you're saying, okay, I want to sample from a normal distribution just to explore the space. What my variance should be? Should it be large? Should it be small? If it's too small, you're making very small moves. If it's too large, you're going to be rejecting a lot. Right? So in that particular case, if you want to keep the rejection rate low, the scale rho here should be on the order of the smallest standard deviation, sigma mean. Right? So it should be on the order of sigma here. Right? Now, for the random walk behavior, the number of steps, separating steps that are approximately independent is going to be of order sigma max divided by sigma mean. So it's going to be on order of this divided by this. Right? If you want to sort of make them a little bit more independent of each other. Yep, question?
Well, but you don't know these sigma mins and sigma maxes.
No, this is just an example.
So you're just guessing this.
Yes, that's right. So in this particular example, if I knew that I'm sampling from the correlated Gaussian, then I can show you that, the number of steps, that's the problem. If you the number of steps is going to be roughly quadratic, right? And that's the typical behavior of the random walk behavior of these methods. So obviously you can see that the specific choice of the proposal can basically greatly affect the performance of the algorithm. Okay? Now, question?
But would there be, let's say you choose, because you don't know about those sigma, so you choose your step size, then you see that, let's say you reject 90% of the time, then you can go something.
Yeah, so good question. So one question is that, let's say you're running your Markov chain, and then you're basically saying, whoa, I'm accepting too much. Right? That means that my sigma is small, increase the sigma. And then, accept, and then say, whoa, I'm rejecting too much, decrease my sigma. The problem with that thing is that it does not define a valid Markov chain. So you have no guarantees that you will converge to the stationary distribution. Because you adaptively, it's not a Markov anymore, right? Because you're looking at the past history and then making decisions of what you want to do in the future. So that creates a problem. There are a class of adaptive MCMC algorithms that study exactly that problem. And there is some theory behind them. You can do adaptation in terms of exploration to figure out what the right thing should be, the right step size should be, but you cannot change dynamically as you run your Markov chain and make a choice what your variance should be in this case. Is the question?
Yeah, just on that point, because that changing the variance is kind of what you'd end up doing in practice, like to make sure it was mixing properly. But I'm saying, if you just start over every time. That's how I learned to do it in the past.
Yeah. So if you're doing a little bit of exploration, figuring out what the right step size should be, and you start again and you're just running Markov chain with specific rho fixed, then that's fine.
Yeah.
All I'm saying is that you can sort of adaptively do it under certain condition, you can, as you run your markov chain, saying, these are
As long as
samples
you
from
do
this.
it, as long as you only keep samples from one value.
That's right. Yeah.
But what if, let's say, you choose two let's say, step size, and then one time out of 10, let's say you use a large step size just to
You
say,
can. Yep. You can define a mixture, for example, right, where certain base operators, they have their own variances, for example, and with some probabilities you're choosing one, you're applying, and you're choosing another, you're applying. Then it's fine. It's just that you cannot make decisions based on how your acceptance rates, like what's the kind of, yeah. Now let's look at the GIP sampler. So GIP sampler is a very popular operator. It's actually a pretty simple one. So let's say you're trying to sample from the joint. You initialize all the variables, and then you loop through the values. So you're sampling the t+1 value for Z1 from its conditional probability, where the other latent variables are fixed to their particular values. Right? So you basically, it's almost like doing coordinate-like sampling. Based on all the other variables, you sample the state. And then, given the new sample state and all the previous ones, you sample Z2, and so forth. So you go in order like that. The key assumption here is that these conditionals you can sample from. Okay? So it might be difficult to sample from the full joint, but from conditionals, it's easy to sample from. Okay? This procedure produces a sample from the required distribution PZ, so it will leave PZ invariant. When you're sampling from this conditional probability of Zn given Zn, given all the other variables, the marginal distribution is basically remains invariant, clearly, because it doesn't change. Right? And each step samples from the correct conditional distribution. Right? So you're actually sampling from the correct conditional. So the joint distribution has to be invariant. Right? That's sort of the intuition why it's invariant. Right? Do you see that? The marginal remains the same. The conditional is from the correct conditional. So the whole marginal has to remain invariant. It has to be the same. So applicability of GIP sampling, so whether you can use GIP sampling operator, it actually depends on how easy it is to sample from the conditional probabilities. Okay? For discrete random variables with a few discrete settings, which is typically the case, you can sample from the conditional, right? Because here, the sum is only performed over the states of one particular random variable. So typically, a random variable might have 100 states, which is okay. You can sum of 100 values, right? For continuous random variables, again, the conditional is going to be given by this expression, and obviously, you have to be able to compute this integral. And the integral typically is univariate and often can be analytically tractable, again, depending on the models you're looking at. Or you can sort of adjust it to standard sampling methods. Every time you're dealing with one-dimensional integrals, it's okay. Yep?
What do you mean by univariate?
Univariate because here you're only performing integral over one dimension.
Oh, sorry.
Over one random variable. So you can think of it as performing integral in one dimension. It also turns out that the GIP sample is a particular instance of Metropolis-Hastings algorithm with the following proposal distribution. Your proposal distribution for a new state, given the old state, is just given by the conditional probability, right, of proposing the new state for the nth random variable, while all the other variables remain the same. So in this case, the components are unchanged by the sampling step, right? Now let's look at the factor that determines the acceptance probability. So in Metropolis-Hastings, right, we designed a transition operator and then we were sampling. There's some probability of accepting or rejecting, right? So what's this transition probability? Well, this is our target distribution ratio of the targets, and this is the ratio of proposals, right? So this is the definition of Metropolis-Hastings. Now let's look at this particular formulation. We can decompose it into the margin, into the conditional times the marginal, conditional times the marginal, right? From that expression here. And what is our proposal? Well, our proposal is nothing more than just proposing the new and the proposing the old. That's the definition. These guys cancel out. These guys cancel out. These guys are the same. Because all variables except for the nth don't change. So it's 1. Which effectively means that its Gibbs sampling is nothing more than the Metropolis-Hastings operator with a specific proposal, which is given by the conditional, and the steps are always accepted. Because the ratio is always 1. Okay? Let's look at the example of a Gibbs sampler. So as with Metropolis-Hastings, we can get some insights into the behavior of Gibbs sampling. So let's look at the correlated Gaussian having a conditional distribution with width L and the marginal distribution of width big L. So this is the width of the whole distribution, and this is the width of the conditional, right? If I'm here, and I'm sampling from this space, that's the width that I'm sampling from. And again, we have a random walk behavior. The typical step size is governed by the conditional distribution is going to be of order L. Effectively, just as in Metropolis-Hastings operators, the number of steps separating two approximately independent samples is going to be of order L over L, big L over small l, squared. So small l is again, if this is my current sample and I'm sampling across Z1, this is how much I can move. That's my variability. Right? If I want to move across this is my variability. It's because I'm doing it in terms of x1, sorry, z1 and z2. If Gaussian distribution were uncorrelated, in fact, if you were sampling from the spherical Gaussian distribution, then the Gibbs sampling would be optimally efficient. Right? Because effectively we'd be sampling from the exact distribution, because 2 dimensions are uncorrelated or independent. One of the tricks that people looked at is this notion of trying to reduce the random walk behavior. That's a big deal in MCMC methods. How do you reduce the random walk behavior? One of these techniques is called over-relaxation. So let's look at the conditional distributions that are Gaussian. Okay? This example again. At each state, the Gaussian of the Gaussian sampler, the conditional distribution is going to be given by this expression. So let's say the conditional is given by the Gaussian. Now, you can have an over-relaxed framework, and that's a very useful technique where the value of Zn is replaced by this expression. Looks awfully complex, right? Where mu here is a sample from normal 0, 1. Okay? For any alpha. Notice what happens here. If I set alpha to 0, this term disappears. This becomes 0. You're basically recovering back Gibbs operator. Right? It's the same. Mean is mu n plus sigma n mu, which is normal mu n sigma n squared. That's the definition of the Gaussian. Right? But one of the key things about this over-relaxed framework is that the step leaves the desired distribution in variance, because if Zn has mean mu n and standard deviation sigma n, Zn prime has also its mean is mu n and its standard deviation is sigma n squared. Right? If you compute the mean and variance of this expression, that's also Gaussian distribution with mean mu n and variance sigma n squared. That's neat, isn't it? For any values of alpha. For any values of alpha. You can compute these quantities. You know, just the intuition here is that the expected value of Zn is mean, mu n, so this term disappears. So the expected value of Zn is mu n. Right? Same thing works for the variance. The variance of Zn is alpha sigma n. So alpha, right? And then this term will cancel. So you have this nice sort of over-relaxed framework. So this, what happens in this case is that for different alphas, you effectively encourage directed motion through the state space when variables are highly correlated. So what happens in this case, we'll just be moving along this dimension in a much more persistent way, which is nice.
Sorry.
Yeah.
So this is true only in the case of Gaussian distribution?
Yes, this is true only if your conditionals are Gaussian.
So is this the best way to sample from Gaussian distribution?
Yep. It's the best way to sample from correlated Gaussians. Yes. Absolutely. If you're working with a model where you have a Gaussian conditionals, that trick it allows you to make more persistent moves in this direction. So you can explore the space much more efficiently. Yeah. But I just wanted to give you one example where people are thinking about how do you design these conditionals, or how do you design these transition operators so that you can avoid the random walk behavior, naive random walk behavior. It's not easy.
And how do you like? What's the framework to prove that this kind of sampling is better than?
It's difficult. There is no particular. You can look at mixing rate, but it's very. In this case, it's very difficult to say which one is better than the other one. We'll come back to that point. For graphical models, remember the conditional distribution is a function of only the states of the nodes in the Markov blanket. So, for example, remember in indirect graphical models, you can have a very complex graphical model with lots of nodes, but this state depends only on the neighbors. Right? So deep sampling could be useful here because given the states of the neighboring nodes, you can sample the state of this node. Right? And you can parallelize across multiple parts of the graphical model. Same thing goes for direct graphical models. And there's a notion of block git sampling. You're choosing blocks of variables so that you can sample them jointly in each block, condition on the remaining variables. So alternatives to git sampling. So let's look at this particular example. So remember at the beginning of the class, we've looked at the Bayesian probabilistic matrix factorization, right? And we've looked at this expression here. The posterior parameters and hyperparameters. And we said that, well, that posterior is pretty complex. What do you do? And it looks like doing some form of Metropolis Hastings and such could be very slow, right? Imagine you have 1 million users and 1 million movies, right? And now you have 1 million times, how many? 30, if you have 30 latent dimensions. So you roughly have 30 million parameters. And now I'm basically telling you, integrate over the 30 million dimensional space. Well, that seems kind of hard, right? You're integrating on the order of 30 million variables. Well, we're going to be using Monte Carlo approximation, right? And the samples here, for making the predictions, are going to be generated by running a Gibbs sampler whose stationary distribution is going to be this posterior distribution of interest. Okay? So we're going to set up a Markov chain whose station distribution is this distribution by essentially using a Gibbs sampler. So this is our Monte Carlo approximation. It turns out that the conditional distributions over user and movie feature vectors are also Gaussian, and they're easy to sample from. It turns out that if I want to sample U, which are my latent variables, conditional on V, which is my other latent variables, so that's the conditional distribution, that has a closed form. It's a Gaussian. Same thing for items or movies. So the conditional distribution over hyperparameters also have closed form distribution. They're easy to sample from. Right? So now you have this particular thing where you have a bunch of latent variables. Conditional on other latent variables, the conditional distribution of one particular latent variable given the other ones has a closed form solution. It's a Gaussian. And it's easy to sample from. And so in this case, this particular model can handle over 100 million ratings. And people have written optimized, parallelized code, and you can basically run this model in 20 minutes. On a machine, you have 100 million ratings, and you basically get answers, which is pretty remarkable. Here's what happens. These are samples from the posterior distribution of a particular movie for particular users with 5 ratings. Okay? So these are samples from the posterior. This is in two-dimensional space, and you can see samples from the posterior. Basically, there is some uncertainty. And variational framework, in this case, works much worse because they're heavy tail. It seems like if you sample from the MCNC, you can sort of get this. If you use variational framework and you set your variational distribution Q will be fully factorized, you can show that it actually becomes a Gaussian, and that would be your approximation, which is not a very good approximation in this case. And then I mentioned to you that this framework is useful because you can get the notion of uncertainty. Right? So here's the uncertainty in predicted values for a test movie. So you take some movie, and you have 4 users. User A has 4 ratings in the system. User B has 23 ratings. User C has 319, and user D has 660. Look at the estimates of the certainties. Right? What this is saying is that for a particular movie, a user that has 660 ratings into the system, the posterior for that user is going to be very sharply picked. So it's almost like doing maximum likelihood estimation. And my prediction is going to be the guy is going to like the movie. It's rating 4, and I'm very confident. For a user that only has 4 ratings in the system, my mean prediction is like 3. But look at my variance. Right? It's pretty big. Right? If I were using just a maximum likelihood estimation, I would say this user kind of going to like the movie. 3 is the user might like the movie. It's like average. Right? But because there is so much uncertainty, that effectively says the user might totally hate the movie or the user might totally like the movie. Right? And this is something you can get from the system by using samples from the posterior. Because for some samples from the posterior, for example, for this particular sample, your prediction is 1. For another sample here, your prediction is 5. Right? So you basically say there's so much uncertainty. I have no idea what the parameter, what the latent preferences of that user are. Right? For some samples, you could hate this movie. For some samples, you can like this movie. For some samples, it's in the middle, which effectively tells you that you basically don't know preferences for that user. Yeah.
For this example, the prior over U and V are Gaussian.
That's right.
So can you sample from the prior and use important sampling to weight the likelihoods?
Yep. Yeah.
How does
Well, no, that becomes much more difficult. You can sample from the prior and just weight by the likelihood. It's you can do that, but it's your estimates are much worse. It's almost like for the predicted distribution, you need to get samples from the posterior, right? If you want to estimate the marginal likelihood, you can get samples from the prior and look at the likelihood.
But if you sample from the prior and then weight it by the product of the likelihood and the function I want to take expectation, that's a valid importance for the sample.
You can use importance sampling. That's true. You can use importance sampling here, but it's nowhere near because you're having lots of different parameters and just using samples from the price and sort of hoping to hit the correct or even reweighting, you'll have a huge variance. So yeah. The last thing that I want to point out for these Monte Carlo methods is this notion of auxiliary variables. Remember, the goal of MCMC is to marginalize variables, but it turns out that sometimes it's useful to introduce new variables or introduce auxiliary variables. Right? So, for example, it seems a little bit counterintuitive, but let's say you're trying to solve this problem. Right? Sometimes it might be useful to actually introduce these auxiliary variables and integrate over this space. Right? So you're actually expanding your integral, and you're integrating over a much larger state space. Or much larger space. Right? So in this case, you join Z and U from the joint, and then you're doing Monte Carlo approximation. Now, we will want to do this if sampling from the conditionals is easy. It might be difficult to sample from Z, but it might be easy to sample from the conditional. Z given U, U given U. And sometimes it might be just easy to deal with this joint as opposed to the marginal. Okay. a lot of different MCMC algorithms use this idea. It's sort of the source of developing new MCMC methods. So one very popular method that's been introduced in the last, I guess, not that long ago. I mean, long ago, I mean like within the last 15 years, is slice sampling. So remember that Metropolis Hastings is sensitive to the step size. It turns out that the slice sampling actually provides you a way of trying to tune adaptive space step sizes automatically. It does it in a nice way, but it also uses this idea of introducing auxiliary variables. So what you're doing here is you're mapping Z with an additional auxiliary variable U, and then you join samples from the joint space. Okay? Now, how it's working is the following. Your goal is to sample uniformly from the area under this distribution. So let's look at this distribution. You have a joint distribution. This is your P of Z. And you have U. And now you're basically saying, you're converting this problem into sampling uniformly. And in this space, and the uniform sample is going to be proportional to 1 of the partition function, and 0 otherwise. So if you look at this expression and say, well, it doesn't make any sense. Why is this corresponds to actually sampling from the target distribution? Right? Let's look at the marginal distribution. The marginal distribution of a Z, if I marginalize out U, right? This is P tilde Z, if I marginalize out U. Well, what is definition? I just plug in the definition here. I'm going to be integrating from 0 to P tilde of Z, right? From 0 to P tilde of Z. That's the range of U, du, right? What is this? I can take the normalizing constant out, and this thing here is nothing more than just P tilde of Z, right? Boom, I get my marginal distribution. Right? So if I take this expression and I integrate with respect to U, the marginal distribution is the correct distribution of interest. So which is the target distribution? Right? That's a key property. That's the way the slice sampling is derived. So now let's see what we can do. Well, the goal is to sample uniformly from the area under this distribution, right? And now we can sort of use the conditionals. We can say given Z, given Z, so if I give you a particular state Z now, we can sample U uniformly from this region. Right? For any given value of Z, you sample U from this region. That's the definition. So what happens here is that, let's say this is the target distribution of interest. For given value Z, you sample U uniformly over this slice. Right, so let's say you sample U here. Obviously, you can compute P tilde of Z. So just uniformly sampling the space, you can sample U here. Now, given U, we sample Z uniformly from the slice through the distribution defined by this expression. Again, comes from here. Right? Given Z, you're sampling this way. So ideally, you'd want to draw samples here or here. Right. And you repeat this procedure. So you're sampling, given Z, you sample U. Given U, you're sampling through the slices. So in practice, slicing directly from a slice might be difficult, so this might be a difficult operation. So you can define a sampling scheme that leaves the distribution invariant. So let's look at the adaptive scheme. Suppose the current state is Z, and we've obtained a corresponding a sample U. So this is U. Then you can define the adaptive scheme. The next value Z is obtained by considering this region. So you have Z means like that. So you have some predefined region. You look at that region, let's say it's region here, and you can sample from that region. In fact, you can adapt the region. You start with the region Z tau, let's say some particular region, having some width W, and then you're linearly stepping out until both points lie outside of your target distribution. Right? So in this case, for example, you can compute lies outside, lies outside. So you have a stepping out procedure. And then you're sampling uniformly in this region, shrinking the region, the slice, if the sample is off the slice, and you can show that that actually satisfies the Dell bounds. I'm not going to show it to you here, but it does satisfy the Dell bounds. It's kind of a nice procedure, right? You start, you have a stepping procedure, you're sampling from it, and then you gradually step out if you're rejecting samples, if the samples lie outside of the slice.
So if you keep sampling from U given Z and Z given U, then isn't it like keep sampling? And
It's like a GIP sampling, but
so do we end up sampling uniformly from the area under the
that's right.
distribution?
That's right. Which is the marginal distribution of interest.
Yes. So why don't we do that, and why do we go through this?
The reason why is because if we sort of go back here, so the question was, sampling from this distribution can sometimes be difficult. Right? So what is this distribution? If we have bimodal here, it's sometimes very hard to sample from these two slices. Right? So you define the adaptive scheme where you say, I guess my slice should be here. Right? And then you sample uniformly from the slice. If you're rejecting, you shrink it up until you actually hit the point which is within the slice, which is within this region here. So it allows you to adaptively choose. Right. So this is one particular example. Of course, it also has the problems, right? And you can see there was a question of multimodality. You have multiple modes. You know, there is no particular magic that this particular algorithm will allow you to find all these modes. You typically will just move around in one mode. And that actually becomes the problem with a lot of MCMC algorithms. Unfortunately, that's it's a very difficult problem. There's no solution to that problem, as far as I know. But there are some questions of using MCMC in practice, right? So the samples that we get from MCMC are not independent. That's one thing, right? They're always dependent, because depending on the state, you're generating a new state given the previous state. So they are dependent. So one question people might ask is that should we theme? So for example, should we keep only every kth step or kth sample? There's a debate on that. Not clear. Probably not. In fact, there were a few papers saying that you should actually take all the samples that you're getting out of your Markov chain. We often start these MCMC at arbitrary starting points. Right? So you start at some point. Should you be discarding a burn-in period? So do you run your Markov chain for some time before you say, now what I'm getting are my samples from the posterior, approximately. Should we perform multiple runs as opposed to one long run? Right? The theory is telling you that you're running your Markov chain, you're performing a very one long run, and eventually you'll reach the station distribution. Practice people start at different points, run multiple Markov chains, and then look at the averaging or competing expectations across these Markov chains. Should we know whether we run out, how long, this is a key question, we actually don't know how long we actually need to run our Markov chain. Have we run it long enough that it actually converges to the station distribution? These are questions that there's no answer. And obviously, the multimodality is one of the biggest questions, right? You start at this point, your Markov chain moves, and you sort of get stuck at this particular mode. How do you go from this mode to this mode? There are methods of doing that, but in general, it's a very, very hard problem, right? So you can get stuck in one mode. It's almost like using, the last lecture, we looked at the mean field, so like finding a single mode, you're characterizing it, right? But not escaping to the other one. Yep?
So you use multiple runs if you know you have multimodal distribution, for example?
Yeah. There's no, it's like one of those things. What if you had 1,000 modes? You're writing 10 Markov chains. Some of them might get stuck in some modes. And then you don't know the relative magnitude of each mode. Let's say this mode is much more probable than this one. Right? You have a Markov chain sort of spends time here, and have a Markov chain spends equal amount of time here. It's kind of hard to calibrate if you can't explore the space. But these are practical. These are sort of like practical problems, as well as theoretical problems of how do you characterize that. So that's why there's sort of two communities Some people prefer to use variational methods because at least with variational methods you can solve it as an optimization problem. You look at the lower bound, you optimize, you reach the convergence, you have convergence guarantees. Say this is when I stop. With Markov chains, there is no, per se, a particular convergence guarantees. You're just running your Markov chain and you're saying, okay, now I'm stopping and this is my answer. So, okay. So that's, yeah.
I was just wondering, when will we not discard the burning phase?
Yeah, it's a good question. I mean, a lot of time people do discard the burning period, but it's not clear how long your burning period should be. Right, so that you can use some diagnostics and such to see whether certain values have converged, but it's all, you know.
Discard the linear.
Yeah.